The last sequence we looked at was an arithmetic sequence. In an arithmetic sequence, each consecutive term differed by the same number. For example, we might have this. All right, this is arithmetic. We start at 5 and add 2. We go to 7. We add 2. We go to 9. We add 2. We go to 11. We add 2. We go to 13, ... and so on. Now, instead of adding the same number to each term, we're going to multiply each current term by some number. So suppose we take this one right here. I'll start at 5, and instead of adding 2, I'm going to multiply by 2. So let's just do it in our heads. We'll get 5 multiplied by 2. We'll get 10 times 2, 20, times 2, 40, times 2, 80, and so on. So in this geometric series, if I look at a term, it's just, in this case, double the term that came before it. Double the term that came before it. Double the term that came before it. Here's what we might think. If you start with that 80 and divide it, because we multiplied, by the term just before it, you get a 2. If you start with a 40, take a look at the term just before it is a 20, make that division, you get 2. You go with a 20 divided by the term just to its left, that's a 10, you get 2. And in fact, if you even take the 10, divide that by the term before it, you get 2. So that happens to every one of these terms, even if I'm way out here. If I take this term, divide it by that term just before it, I'll get 2. There's a name for this 2. This is called the common ratio. You may remember when we were doing our work with arithmetic sequences, the difference between each term, that was called the common difference. But now since we're multiplying, when we go backwards like this, we get quotients, it's called the common ratio. And we're going to denote that with the letter R. We use R for ratio. You remember back here when we were doing arithmetic sequences series, we used D for common difference. So I'll just make a note of that. When we were working with arithmetic, it was called the common difference, and that was a lowercase d. And when we were working with geometric, we call it a common ratio and use a lowercase r. I like to develop a formula for getting the next term or the nth term of a geometric sequence. So let's look at ours and rewrite it in a different way. I'll start with a 5. All right, leave a little space here. That'll be the first term. Then how do I get the second term? Well, the second term, what I'm going to do is take that 5, multiply it by the common ratio, which is 2. It'll look like this, 5 times 2. How do I get the third term? Third term I get by taking the current term, the second term, right, the one just before it, and multiplying it by 2. So that looks like this. 5 times 2, there's the second term, times 2 again. Now I'm not going to simplify these. I'm looking for a pattern. So when you're looking for a pattern, try not to simplify because you lose some details. So how do you get to the fourth term? So to get to the fourth term, you take the third term, right here, times 2. So this is going to be 5 times 2 times 2, that's the third term, times 2. We'll do one more. What about this fifth term here? To get the fifth term, we're going to take the fourth term right here, times 2. So it'll be the fourth term. I'll write that 5 times, and then there's 3 2's there, times 2. So let's go back here and see what exactly it is that we did to get from one term to the next. So the first term here, we started with a 5 and didn't do anything to it, right? So we just had 5. Then we got to the second term. So what did we do? Well, we took our 5, the previous term, and we multiplied it by 2 just one time, all right? So nothing really new there. But then what do we do to get to the third term? To get to the third term, we took the second term right here. There's the second term, and then we multiplied it by 2 again. Now, do you see what this 2 times 2 is? Isn't that just 2 squared? So I'm going to kind of compact the notation here and write this. We had 5 times, well, we had 2 of the 2's, so I'll have 2 squared. Now, what about the third term, or the fourth term? The fourth term, we had our 5, and then 2 times 2 times 2. Well, there's 3 2's being multiplied, so that's going to be 5 times 2 cubed. And you can see the fifth one now, can't you? I think so. 5 times 2, there's 4 of them there. So look at this pattern that we've developed here. At the first term, I don't have any 2's. At the second term, I have 2 one time. At the third term, I have 2 twice, right? I have 2 of those common ratios. At the fourth term, I have 3 of the common ratios. At the fifth term, I have 4 of those common ratios. So let's make a guess here. Based on that pattern, what do you think the sixth term here will be? Well, I'm thinking it's going to be a 5 times 2, and how many of those common ratios? Well, it looks like the number of common ratios, right, that's the number in the exponent, number of common ratios is 1 less than the term number. 3, 1 less than 4. 2, 1 less than 2. 2, 1 less, 1 less than 2. And there's none here. 0 is 1 less than 1. So I'm guessing over here that this should be 1 less than 6 is a 5. Now, what if we just kept on going? 7, 8, 9, 10. Let's look at that one, actually. Let's look at the 10th term. What if we're here at the 10th term? Can you make a guess of what we're going to write for this one? I think it's going to be 5 times. Now, it's going to be times 2. And how many 2's? Well, the pattern suggests that the number of 2's, the number of common ratios, is always 1 less than the term number. So at term 10, 1 less is going to be a 9. So I'm thinking that that's going to be a 9. Now let's keep going. Dot, dot, dot. Now we're out here at some general term, the nth term. So what do you think we should write here? I think it should be a 5 times 2. Now the question is, what do we put here? Well, we have a pretty good idea. It's going to be 1 less than this. So this is n. 1 less than n we describe with n minus 1. So for this one, I'm going to write n minus 1. I think we're ready to write a general term here. So the general term, here's a sequence down here. I'll write it down here. Suppose we have this sequence here. You have A1, the first term. Then you have A2, the second term. A3, A4, the third term, the fourth term, and so on. Dot, dot, dot. Then you have the nth term. And what we want to do is we want to describe this nth term in terms of, say, the first term and the common ratio. So let's write a formula for this. Maybe we could write it like this. A sub n, this will be the nth term. What is A sub n? So look back to see what we did. It sure seems in each case up here, what I did is I started with the first term, right? 5, 5, 5, 5. So I started with a 5. So in our general case, we'll start with the first term, A1, and then we multiplied it by what? We multiplied it by, say, the common ratio, common ratio, common ratio, and common ratio, but the exponent on the common ratio was always 1 less than the term number. So I think I'm going to write this. This will be A1 times the common ratio raised to what power? All right, 1 less, here's the term number, n. What are you going to write here? It's going to be n minus 1, right? Because you have n minus 1 of the common ratios. So this is going to be n minus 1. And there's our formula for the nth term of a geometric sequence. Let's take a look at an example here. Now, I'm kind of out of space here, so I'm going to erase this stuff. We could always rewind to get back if we needed that. But let's look at an example. Let's do this. Let's find the 11th term of the example sequence. All right, here's our example sequence up here. So let's find the 11th term. So the 11th term is described with the notation A sub 11. And, all right, what are we going to write here? Well, what does our formula say? Start with the first term. Now, our first term is a 5. Multiply it by what? The common ratio, which in our case is 2. So we'll multiply it by 2. But how many of those? Well, according to the formula, it is 1 less than the term number. Our term number is 11, so this is going to be 1 less. So, you know what? I'll write that here. It's going to be 11 minus 1. So what we get is A sub 11, the 11th term, is 5 times 2 to the 10th. Now, as it turns out, A sub 11 is 5 times 2 to the 10th is 1024. And then 5 times 1024, a sub 11, is 5120. 5120. Now suppose we've got a geometric sequence and we want to add up the first n terms. Like suppose in our last example, we wanted to add up the first 20 terms of that geometric sequence. Well, there's a formula for it. I'm not going to develop this formula. I'm just going to write it. I'm going to write it like this. S sub n, and it means this. S for sum. The sum of the first n terms. And here's how we get it. This is equal to this fraction. Now in the numerator, here's what you put. The first term, a sub 1. Then you multiply it by this. The common ratio to the n, and that n matches that n. So if you want the 15th term, that would be a 15. And then minus 1. And then in the denominator is r minus 1. Common ratio minus 1. Let's do an example here. Here's our example geometric sequence. 5, and then we're doubling everything, right? 5, 10, 20, 40, 80, dot, dot, dot. And if we want to find, say, S sub 11, right, what we're going to do is add up the first 11 terms. Let's just add up the first 11 terms. So we have a formula for this. Formula is right here. So S sub 11. So I'm going to add up the first 11 terms. Here's how I do it. Fraction. What's the formula say? A1. That's the first term. So this is going to be a 5. Raised times. All right. What is this? This is the common ratio. And ours is 2, right? So ours is a 2. Raised to the n, right? I'm up here. I'm looking at my formula, n. And n for us is 11. So 2 to the 11th, but then minus 1. And in the denominator, it's r, 2, minus 1. Okay, now it's just an arithmetic problem. So let's see. I'm going to get out of this 5 times, all right, 2 to the 11 is 2048 minus 1 all over 2 minus 1 is a 1. All right, now this is 2048 minus 1 is 2047. So if I take 2047, multiply it by 5, I'm getting this. So S sub 11 is 10235 all over 1. Or how about just, we don't need the 1 there. So the sum of the first 11 terms is 10,235. Here is an amazing result. If we have an infinite geometric sequence, that means it just goes on forever, that sometimes we can actually find a finite sum. We can actually add up an infinite number of terms and get a value for that. Here's a numerical example. Suppose we start with our series, say with 1/4, and then we're just going to multiply each consecutive term by a half. We'll just cut each term in half. So the next one would be what? 1/8, 1/16, 1/32, 1/32, 1/64, dot, 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 right? Just on and on and on. So this is a geometric sequence because how do I get from one term to the next? I multiply the current term by 1/2. So in this case, r equals 1/2, and this is going to be infinite because it goes on forever. I'm going to add these up. It's going to look like this. 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/32 plus 1/64 plus dot, dot, dot forever. Well, now here is an amazing formula. It is amazing. Here's what this says. If a geometric sequence has the first term a1, right, first term, and if the common ratio is a fraction between -1 and 1, right, now -1 and 1, sometimes you'll see it like this. The absolute value is less than -1, which means -1 less than or less than 1. So if you have a geometric sequence and the common ratio is between -1 and 1, you can add up all infinitely many terms using that formula right there. What does it say? Just take the first term, divide it by 1 minus the common ratio. Now, we're not going to develop it here. If you want to see how it's developed and a proof for this, it's in the textbook, and you can find that in section 8.4. We'll just use it right now. So in our example, right, let me circle this so I don't lose it. Yep, let me circle it so I don't lose it. So here's what we'll have. S sub infinity, the sum of all infinitely many terms, right? Just take this one right up here, add these up. So just keep going all the way out and all the way out. So it looks like this. What do we get? A1, the first term, 1/4, divided by 1 minus the common ratio, which is a half. So what do we get here? We get 1/4 divided by, right, 1 minus a half is a half. So this is 1/4 times, what do we get here? Divide by half, so you multiply 2 over 1. So we get 2 over 4. So S sub infinity is equal to 1/2. Isn't this just astonishing that you can actually do this? You can actually add up an infinite number of numbers and get a finite result. It seems anti-intuitive, right? Because what are you doing up here? Well, it seems like you've always got a little bit more to add, right? You can always add half the next one. It just seems like you never get there. But let me offer some kind of an idea why it might work. Suppose wherever you are right now, this is where you are at right now. And then what you want to do is you want to get maybe to some door. All right, so here's where you are. Here's a door. And you want to get from here to here. So what do you have to do? Well, to get from where you are to the door, you have to go halfway to the door. Then, when you're at that point, you have to go halfway again. So what have you done so far? You've traveled halfway. Then you travel 1/4 of the way, right? So this right here is 1/4. Then, now you're here. Then you have to go here. So that's halfway again. So that's halfway again. Now that distance is 1/8, and then that distance is 1/16, right? So you're thinking, all right, I have to go from where I am to get to the door, I have to go halfway. Then I have to go halfway again, then halfway again, then halfway again. Intuitively, it seems like you never make it to the door, but you know you make it to the door. And suppose now that that distance, you just call that a 1. So then what have you just done? You've taken half, because you've gone halfway, then 1/4 of the way, then 1/8 of the way, then 1/16 of the way, then ... and what do you get? You get exactly 1. It's just amazing.